We all think we know what work is, right? It's that feeling after a long day at the office or grinding away studying for a big exam. But it turns out in the world of physics, the word work means something very specific. And honestly, it's pretty counterintuitive. So let's get into it.
So let me ask you this. When you feel like you're working your absolute hardest, are you actually doing any work? I mean, according to a physicist. By the time we're done here, you might be really surprised by the answer.
Okay, check out these two pictures. On one side, you've got someone pushing a car that's actually moving. On the other, a weightlifter holding an incredibly heavy barbell perfectly still over their head. Now, in which case is work being done? I mean, your muscles are probably on fire in both scenarios, but a physicist would look at this and say, nope, work is only being done on that car. So why? That's the big question we're going to answer today.
To figure this out, we have to kind of reset our brains and redefine what work even is. And it really all boils down to two key ingredients.
First up, you need a force. Now, this part makes total sense. It's a push or a pull on something. When you shove a box across the floor, you're applying a force. When you lift a dumbbell, you're applying a force. This is the effort part of the equation, the part we can all feel.
But here's the second ingredient, and this is where physics gets a little picky. It's called displacement. And all that means is that the object's position has to change. It has to physically move from point A to point B. If nothing moves, there's zero displacement. That part is absolutely non-negotiable.
So, you put those two together, and you get the golden rule of physics work. For work to be done, a force has to be applied, and that force has to make something move. You need both. No exceptions. And that, right there, is why holding a heavy weight perfectly still, no matter how exhausting it feels, results in zero work being done on the weight.
Okay, so we've got the concepts down. Now, let's see how scientists actually put these pieces together with a simple but really powerful formula.
And here it is. The formula for work is W equals F dot delta R. Now hang on, that little dot in the middle is super important. It's not just regular multiplication. It's what's called a dot product, which is a fancy way of saying that the direction of the push and the direction of the movement both matter.
So let's break that down into a version that's a little more friendly. Work, that's the W, equals the strength of the force, or F, times the distance of the displacement, delta R, times this thing called the cosine of theta. And all theta is the angle between the direction you're pushing and the direction the object is actually going.
And honestly, that cosine theta part is the secret sauce. It's the key to the whole thing. What it means is that only the part of your force that's pointing in the exact same direction as the motion actually counts as work. So if you're pulling a little red wagon with a rope that's angled up, some of your effort is pulling up and some is pulling forward. Physics says only the forward part of your pull is doing any real work.
So how do we even measure this stuff? Well, the standard unit for both work and energy is the joule, and we just write that with a capital J. To give you an idea, 1 joule is the amount of work you do when you use 1 newton of force to move something 1 meter. So a joule is really just a newton meter.
All right, now that we've got the formula, we can dig a little deeper into the rules of the game. Because it turns out work isn't just a yes or no thing. It can actually be positive, negative, or just plain zero. So when is work zero? Well, we already know the first one, right? You push with all your might against a brick wall. You're using force, but the wall doesn't move. No displacement means no work. But the second case is way cooler. If your force is perfectly perpendicular, at a 90-degree angle to the motion, the work is also zero. Think about a satellite in a perfectly circular orbit around Earth. Gravity is pulling it straight down toward the center, but the satellite is moving forward, exactly perpendicular to that pull. The work done by gravity on that satellite? Zero. And that brings us to positive and negative work. This is all about energy transfer. See, you do positive work when your force helps the motion, like when you push a car to get it going. You're literally transferring your energy to the car. But you do negative work when your force opposes the motion. The best example is friction. It's a force that fights against the car's movement, slowing it down by taking energy away from the system, usually by turning it into heat.
Okay, enough with the theory. That's all great, but let's put this stuff into practice and see how it all adds up with a pretty mind-blowing real-world example. You are not going to believe this. Back in 1990, a guy named Walter Arfier lifted 281.5 kilograms. That's over 600 pounds. And he lifted it a distance of 17.1 centimeters. Oh, and one more thing. He did it all with his teeth. Just his teeth. That is an insane amount of force. But how much work did he do? So let's lay out the facts here. We know the mass of the object, 281.5 kilos. And we know the distance he lifted it, which is 17.1 centimeters. First thing we have to do is convert that to meters, so that's 0.171 meters. Now we can figure out the work.
All right, step one, we need the force. To even lift that thing, he had to apply an upward force that was at least equal to its weight. And we find that by multiplying the mass by the acceleration due to gravity, which is always 9.81 meters per second squared here on Earth. So 281.5 kilos times 9.81 gives us a force of 2,761.5 newtons.
Now for the easy part, step 2. We just multiply that force by the displacement. Since he lifted it straight up, the force and the displacement are in the exact same direction. That means the angle is 0, and the cosine of 0 is just 1. So we multiply 2,761.5 newtons by 0.171 meters, and we get our final answer, 472.2 joules of work.
So what is that number? 472.2 joules, what does it actually represent? Well, here's the most important takeaway of all. Work is energy. It's not just some abstract number from a formula. It's a direct measurement of energy being transferred from one thing to another.
Which leaves us with one last really interesting question to think about. We just calculated that Walter Arfiel did 472.2 joules of work on that huge weight. He transferred that much energy into it. So where did all that energy go? Well, the answer has to do with another huge concept in physics, potential energy. But that is a story for another time.